Phil has worked in the transformer industry since 2011. His areas of interest include condition monitoring of power transformers through oil analysis, thermography, visual inspection, and electrical testing, plus life extension via oil filtration. In his role as Oil Services Manager, Phil's focus is on providing technical support to our customers. His experience is also leveraged across the Ampcontrol group in relation to transformer oil testing, oil analysis, condition assessment, oil filtration, and alternative fluids, including natural and synthetics. This also includes the development of a digital asset management platform and is an extension of his work at Shell Oil in the UK and the Netherlands. Earlier in his career, Phil held a number of scientific-related and research posts in the UK and holds both a bachelor and master's in biochemistry. So please welcome Phil.
Thanks, Emily. Good afternoon, everybody. Welcome to this webinar from Ampcontrol. The presentation is called Oil Analysis, Testing On-Load Tap Changes and Managing Corrosive Sulphur in Transformers. So we hope you find the webinar useful. Its purpose is to offer you some practical guidance on working with transformers. So what I'd like to cover today is listed here. I'll talk about transformer reliability very quickly, including the on-load tap changer and how we understand on-load tap changer condition during operation. And then I'll move on to corrosive sulphur in transformers, how we assess the condition of how we identify the problem by oil testing. I'll talk about risk factors and also mitigation techniques. And both of these subjects, the OLTC testing and corrosive sulphur, have come up in conversation recently in my dealings with the asset managers that we work with. So let's start with reliability. So we know that transformers are reliable pieces of equipment, and reliability surveys are consistent in outlining their low failure rate, which is less than 1% across all voltage classes. The reliability of a transformer is a product of the reliability of each single component. So not only the main transformer tank itself, but also the bushings, the cable box, and the tap changer, etc. And in substation type transformers, the main location of failures are in the windings, the load tap changer, and the bushings. And these three items, three components, in one survey I looked at, accounted for 80% of failures. And according to CIGRE Technical Brochure 642, which is a transformer reliability survey that you can download from the web, they saw that up to 50% of all transformer failures are due to the on-load tap changer, between 10 to 50%. And the differences in the numbers are due to the different voltage classes of the transformer, the application of the transformer, and also the maintenance policies of the asset manager. The table on the right is taken from this particular CIGRE reliability survey, and it quite nicely shows you how the frequency of the failure location changes according to the different voltage classes. So with the tap changer, for instance, there's quite a big increase in the percentage of failures in the tap changer as the voltage increases from this to this. So how do we understand the condition of an on-load tap changer during operation? So as with transformers, the more information we have about condition, the more opportunities we have to intervene to avoid failures. And the image on the right outlines different problems that can develop in on-load tap changes during operations, so they're listed here. And also the effectiveness of available condition monitoring techniques in detecting and managing these problems. So this table on the right was taken from this technical brochure, Condition Assessment of Power Transformers from CIGRE. Now, I guess we'll begin with dissolved gas analysis. This is a test that we perform on an oil sample. It's effective at detecting and monitoring arcing and overheating problems. And a recommendation that we provide where we come across these problems, certainly overheating and coking problems, is to do thermography. And thermography is quite effective in tap changes that have a tank that's bolted onto the main tank. So these are compartment type transformers. Now, according to this chart, dissolved gas analysis isn't effective at evaluating contact wear. However, another oil test that we can perform from an oil sample is particle counting and also wear metal analysis. And these tests can be used to evaluate contact wear in on-load tap changes. And the condition assessment program should include more than just one technique to cover the widest possible ranges of failure. So do consider sampling your on-load tap changer every year. An oil sample can help you identify problems. It doesn't cost much, and it doesn't involve taking the equipment offline, and the sample can be taken when the transformers are being sampled. So we run a NATA accredited oil test facility in Newcastle. The company is Verico. It's an independent test organization within the Ampcontrol group. On the left, I've listed the common tests we perform on oil samples from on-load tap changes. So typically, you do these once per year. Dissolved gas analysis is a key test, and I'll talk about this on the next couple of pages. Breakdown voltage, this is a test that we do on transformers also. And as in transformers, dielectric strength of the oil should be above a certain level for continued safe use of the asset. And using online filters or changing the oil can help with issues caused by high levels of moisture and particles, which can affect the breakdown voltage. Elevated water levels can reduce the breakdown voltage of the oil and accelerate aging of the contacts. If the on-load tap changer is a free-breathing design, we recommend you regularly inspect the silica gel breather to prevent admittance of humid air. And oil can be replaced during scheduled maintenance if problems exist. Very high levels of acid are suspected of causing corrosion of silver contacts in a tap changer. So this should be avoided because failures of the on-load tap changer can occur if silver sulfide deposits flake off and migrate through the asset. It's advisable to conduct annual particle counting to monitor wear of contacts, and increases in larger particles can be an indicator of advanced deterioration. And we use the silver sulfide test to evaluate whether the oil is corrosive to silver contacts in the tap changer, and I'll talk more about this a bit later on. So let's look at dissolved gas analysis in a bit more detail. So dissolved gas analysis, DGA, has been used to monitor transformer condition since the 1960s, and the test can also be applied to understanding the condition of on-load tap changes. And it's a lot more complicated than transformer DGA. We recommend, like with transformers, you use a 50 ml glass syringe so we can provide you with a more accurate condition assessment. Now, we use IEEE C57139 in the first instance to help us interpret the test data. In the results, we look for these problems. So mild overheating, higher temperature overheating between 300 and 700 degrees Celsius, and high temperature heating above 700 degrees Celsius. Also abnormal arcing. We can use Duval Triangle 2 to help us interpret the data, and there are two versions according to whether the tap changer is a compartment type or an in-tank type. We also can use changes in the ratio of gases, in particular ethylene and acetylene, to help us detect problems such as coking or deterioration of oil-immersed arcing contacts. So we record the dissolved gas analysis data from every on-load tap changer test that we do. And as per guidance from IEEE C57, we maintain a database that includes dissolved gas analysis information and also manufacturer and model. So this allows us to monitor changes in the gas ratios, which help us to identify problems, and also allows us to benchmark the performance of specific manufacturers and models. So this particular classification system exists for different manufacturers and models of on-load tap changes, and it's based upon the operation of the on-load tap changer. And we see different manufacturers over here, the different types, and then their classification. So an asset that we frequently test is the Rheinhausen M, and this is a ARS type tap changer. And what this means is that the arc breaks in the oil, bridging current occurs through resistors, and the diverter switch and the tap selector are in different oil compartments. And these different modes of operation, according to the different manufacturers and even the models, are why the results are more difficult to interpret than transformer DGA. So we have this classification system to work with, and we also have this these guidelines, these useful guidelines to work with, and these outline the rate of gas generation during normal operation per 1,000 operations according to the different types of tap changer. So these are documented. This is documented in this technical brochure from CIGRE, so brochure 443. So to provide an accurate condition assessment, so we need to know what the manufacturer is, what the model is, and also the number of operations. So I'll finish off this section with a case study for an on-load tap changer. So I know what the manufacturer is and what the model is. It's an ARS type on-load tap changer, and we sample this tap changer every year. And I've not included the actual DGA results, but the numbers are actually much higher than what you would typically see in a transformer, and this can be normal for a tap changer. But what I've listed here is the summary of the results, and we'll go through these now. So the output of Duval Triangle 2 in 2019 and 20 is X3. So this means there's possibly a high temperature heating problem or abnormal severe arcing. But what we've seen is that the acetylene levels have actually reduced between 2019 and 2020. And so this really discounts the occurrence of abnormal severe arcing. And the ethylene to acetylene ratio has increased slightly between 2019 and 2020. So this could indicate increased thermal activity in the on-load tap changer. However, overall, the total dissolved combustible gases, so this is the sum of the concentrations of hydrogen, methane, ethane, ethylene, acetylene, and carbon monoxide, these have reduced in 2019 and again in 2020. So in terms of a fault, this is very positive. So I was also able to determine that the rate of generation of gases, 1,000 operations, was less than 6,000. And so this level of gassing is considered normal for an ARS type on-load tap changer. And also normal operation generating elevated ethylene to acetylene ratios has been documented for ARS type on-load tap changers. And if you're presented with dissolved gas analysis results for your tap changer, and they indicate problems, also remember that to confirm faulty operation, the actual part per million gases formed per operation should be significantly higher, i.e. more than 50% than those observed during normal operation. And this guidance comes from CIGRE. And in this instance, I don't really believe that we're seeing a problem, even though some of the indicators point to a fault. So if the DGA results for your tap changer indicate a heating problem, which can be related to the burning of contacts, for instance, so we recommend you consider the following. So do more frequent dissolved gas analysis to determine the rates of generation of the gases, monitor the rate of generation per operation, and monitor for increases in the ethylene to acetylene ratio. You can consider electrical testing, such as static winding resistance, dynamic winding resistance. You can do a thermography survey for certain types of tap changer, and also do an internal inspection to look for burned contacts. And the image on the right was taken from a CIGRE technical brochure, and it's an ABB in-tank on-load tap changer with burned contacts. So the next part of the presentation is about corrosive sulfur in transformers. So corrosive sulfur related transformer failures have been reported around the world since the 1990s. The frequency of failure is low, but the phenomenon has caught the attention of transformer managers because the failures are unexpected, and big industrial and generator step-up type transformers have been involved. So here are some very quick headlines about corrosive sulfur. Oxidation inhibitors. are added to transform a mineral oil to improve oxidation stability. Their inhibition of oxidation slows the aging process of the oil, which is good for the transformer. Under certain conditions, the oxidation inhibitors, which are rich in sulfur, can become corrosive for copper and silver surfaces in the transformer. Copper windings are an example, and also so are silver-plated contacts of the load tap changer selector switches. A recognized candidate is DBDS, which is dibenzyl disulfide, and it's likely there are others. So many oils sampled from failures due to the corrosive sulfur problem have had DBDS present. So DBDS reaction at the windings can produce copper sulfide deposits on copper surfaces. It can also lead to copper sulfide deposits being formed on the paper insulation, including in the windings. And copper sulfide is a grey-black solid with high conductivity, which weakens the dielectric strength of the oil-immersed paper, and it reduces the insulation resistance of the paper. And copper sulfide deposits on the paper insulation can lead to a conductive path, and this can lead to a failure. Also, deposits on bare metal surfaces can also cause overheating. So let's quickly go through this case study. So we're looking at the test results from a 6 MVA, 66 kV transformer manufactured in 1979. There are two of them. We see no problems identified by the dissolved gas analysis results. And the moisture levels on the whole are pretty, the oil test results, the oil quality results on the whole are pretty good. And the paper insulation condition shows no significant degradation. So the DP, degree of polymerization, is 803. So really above 600, 650, we still think that the paper insulation condition is almost as new. So the particle count results were quite interesting. These came back showing high levels of contamination in the oil, which indicates abnormal operating conditions. So we had the oil transformer resampled, and the retest results came back with a big improvement in the particle count results. So we think there must have been a lot of material in the sampling valve, and it needed a second flush to clear the drain valve. So we'll monitor the particle levels when we resample the transformer in the future. And we did some corrosive sulfur testing. So we started with the IEC 62535 test, and this returned a positive result. So yeah, we then followed this up with measurement of DBDS concentration. And the concentration was low, and DBDS, as I said, is a candidate for causing corrosive sulfur. So something else in the oil perhaps has given a positive corrosive sulfur result. And we also did the ASTM D1275 silver corrosion test, and this also returned a positive result. So something in the oil is also corrosive to silver. And the significance of this is that this could lead up to a buildup of silver sulfide on the silver-plated contacts. In 2019, CIGRE published a technical brochure called Condition Assessment of Power Transformers. The publication outlines development of an asset health index system that can be used to assign a condition score to an asset. Here we're looking at the summary table for mineral oil. So the process uses a color-coded scoring matrix that provides a condition assessment and recommendations. And it ranges from no deterioration all the way up to de-energize as soon as possible, don't return to service until the problem is repaired. So their guidance on corrosive sulfur is listed here. So where a transformer has a positive corrosive sulfur result, they give an F assessment, which means de-energize as soon as possible and don't return to service until the problem is repaired. Now, we manufacture transformers here in Australia, and the photo on the left is a picture of the internals of a transformer we were manufacturing at our transformer factory in Newcastle. So note the paper-covered windings. Paper is wound around a copper conductor, and the windings are wrapped around a steel core. And the middle photo is a close-up and cross-section of the paper-covered windings. So I took this photo while I was on a tour of our factory. I was given permission by our transformer factory manager, Cal Pesh. So copper sulfide can simultaneously form on the surface of the copper windings and also on the paper insulation. And it can also form independently on either. And the photo on the right is from a failed transformer. So it's not one of our transformers. It's a failed transformer. And we can see the copper conductor is tarnished with corrosive silver sulfide. It's tarnished with silver sulfide. So contrast the color of the copper here in a new transformer and when it's got copper sulfide deposits on it. And what we're looking at here are the inner layers of paper and then more outer layers of paper. And we can see copper sulfide deposits on the innermost layers of the paper and less so as we move away from the conductor. So this indicates migration of copper sulfide from the copper conductor through the paper. And a copper sulfide deposit on the paper insulation can lead to a conductive path, and this can lead to a failure. Now, on the left, I've listed tests that we can perform on an oil sample from your transformers to help us understand the corrosive sulfur status of the oil, and therefore the risk profile of your transformer. So the IEC 62535 test is a good place to start. So we incubate your oil sample with some copper and kraft paper for 72 hours at 150 degrees Celsius. And if we see very dark tarnishing of the copper and the paper, this tells us that the oil is corrosive. If we give you a positive result in this test, we then recommend that you do additional testing to further understand the extent of the problem. So the DIN 51353 test looks at silver sulfide in transformer oil. So if the oil is corrosive to this test, it could spell problems for the silver contacts in the transformer and the tap changer. And also we might give you recommendations to evaluate the DBDS levels and also the passivator levels in the oil. We can also look at the dissolved gas analysis results to see if any heating is occurring in the main tank. So this may be being caused by corrosive sulfur deposits, and deposits of sulfides on bare copper and silver surfaces in the transformer can lead to increases in resistance and so overheating. So my intention is that the information on this page, risk factors, will give you some idea of the risk profile of your asset. So firstly, look at the age of your transformer. Now, a manufacture date between 1990 and 2010 means that your transformer might contain corrosive mineral oil. After this time, due to awareness of the problem, corrosive oils were thought to have been or were increasingly removed from the market. So do an IEC 62535 corrosive sulfur test, and if the result is positive, your transformer is at a higher risk. Then look at the dissolved oxygen levels in the oil. So at normal transformer operating temperatures, copper sulfide formation is higher in a low oxygen environment, such as in a sealed transformer or a free-breathing asset with a bladder in the conservator. At higher operating temperatures, which could be during overload conditions, copper sulfide formation can occur in both low and high oxygen levels, but deposition on the paper at these higher temperatures is more prevalent in a high oxygen environment. So the picture is a bit complicated. And based on failure studies to date, the transformers most commonly affected are generator step-up transformers greater than 100 MVA, high voltage transmission transformers, and also industrial and rectifier transformers. And the picture on the right is from a transformer post-mortem taken from a CIGRE technical brochure at 625. And they found an interturn fault in the HV winding. So the paper insulation in the area in this winding was typically greater than 600. So paper degradation was not believed to be the cause of the problem. And the only significant factor they found during the scrapping of the transformer was the presence of copper sulfide deposits. So if you have corrosive sulfur in the oil in your transformers, a number of mitigation techniques exist to prevent the problem from getting any worse. So the following techniques really are not effective on already contaminated windings and bare metal surfaces. So you can increase the operation of your fans and your pumps in the transformers, or reduce the temperature settings for the cooling fans to be switched on. So overheating can increase copper sulfide deposition, and so can increase the risk of failure. Now we can treat the oil, and one way is to add metal passivators. So these are chemicals that can be added to transformer oil while the transformer's online. These stick to non-enameled bare copper surfaces. They form a protective layer on the surfaces of the copper windings, and they prevent further copper sulfide formation. And immediately after you passivate the oil, you should repeat the IEC 62535 corrosive sulfur test and confirm a negative result. Once you add passivator, it's important to monitor passivator concentration in the oil every 12 months, and you need to maintain levels above 100 parts per million. Also, we recommend that you don't add passivator to oils containing high levels of acid. So we believe that high levels of acid can affect passivator stability and reduce suppression of copper sulfide formation. So consider oil reclamation via full as earth treatment prior to passivation if the acid levels are elevated. And another reason to do oil reclamation is that you can reduce the DBDS levels in the oil with the process. So remember that DBDS is a strong candidate for causing copper sulfide formation. Unfortunately, addition of passivator is not able to protect against the corrosion of silver-plated contacts in the tap changer or the transformer. And this particular corrosion is caused by elemental sulfur, another reactive sulfur species. And the source of these is thought to be from oil reclamation that isn't performed correctly. So after oil reclamation, it's a good idea to check the oil for corrosive sulfur and also DBDS concentration. And if the oil is silver corrosive, or if the passivator levels continue to decline, this suggests an active corrosive sulfur problem, and a long-term solution is to replace the oil. And after you change the oil, after 12 months, if the DBDS levels are still greater than 20 ppm, because the DBDS could seep out of the windings, then you need to think about oil reclamation to reduce the DBDS levels. So this is the final page. I've got a couple more minutes to go. So I'll finish off quickly going through this risk assessment that you can perform yourselves. This was also taken from CIGRE Technical Brochure 625. So think about questions 1 and 2. Is the oil corrosive? Is DBDS concentration less than 20 mg per kg? If the answer to questions 1 and 2 are no, the probability of copper sulfide deposition is 0 and there are no actions. If the answers to 1 and 2 are yes, then we need to look at questions 3 and 4. So does DGA indicate overheating? Is the transformer highly loaded? If the answer is no, the probability of copper sulfide deposition is low. If overheating is indicated, or if the transformer is highly loaded, then we need to look at oxygen levels in the oil and whether oxygen consumption is occurring. So if oxygen levels are low and passivator hasn't been added, the probability of copper sulfide deposition is thought to be high. If passivator has been added, but if it was added after the first year of service, the probability of copper sulfide deposition is still thought to be high. And if we add passivator and levels are not stable, even after repeat cycles of passivation, the probability of copper sulfide deposition is thought to be high. And in these circumstances, we really need to look at an oil change and then continue to monitor the situation with the IEC 62535 test, DBDS, and also passivator levels. So this is a perceived long-term solution for highly loaded transformers with a high winding temperature and low oxygen levels. And following an oil change, if the oil is not corrosive and passivator levels remain stable, you can be confident, or there's a high degree of confidence, that you've reduced the risk of copper sulfide deposition, which is good. So there you go. Hope you found the presentation useful. You can email me with any questions, and here is my email address, and you're welcome to send me any oil analysis results that indicate problems. So thank you.
So Phil, we might jump into the questions. We've had a couple of people ask. So the first one, and you may have already answered this during the risk assessment in your previous slide, but is high trending of ethane an indicator of corrosive sulphur presence? And that was from Rahman.
Look, it can be, because ethane is produced by, for instance, stray gassing or low temperature overheating. So it's possible that the ethane is being produced by being copper sulfide deposits on bare metal, for instance. So certainly where I come across, when we do oil tests and I see overheating or some forms of heating, which you'll see this in the dissolved gas analysis by, for instance, production of ethane, then the recommendations that I'll provide are think about doing a corrosive sulfur test just to confirm that there is no corrosive sulfur in the oil.
The next question from Thomas was, I may have missed it, but what was the outcome of the case study where the transformer showed a corrosive level of sulfur and thus was recommended for immediate de-energization?
Essentially, these transformers are on a site that's in care and maintenance at the moment. So before the transformers are re-energized and put into service, we think the recommendation that we've made is to change the oil. And so that will happen, we think, before the transformers go into operation again.
Here's one that's come through. Can you share again the minimum value DGA and oil characteristics for the on-load tap changes?
Yeah, so let me just go back. So we use this particular standard, IEEE C57139. And there is, with a transformer, different types of transformers, there are different acceptable levels for particular gases. We don't really have this for on-load tap changes. They just operate in such a different way according to the manufacturer. So we have this different classification system, and we look at really what's important is looking at the results, the actual part per million levels of the total combustible dissolved gas levels. So that's a combination of hydrogen, methane, ethane, ethylene, acetylene, carbon monoxide. And we have to really look at the number of operations between the samples and then confirm that the levels are below these levels. And then we also look at the fact we need to compare the levels. If we think there's a fault, we need to compare the levels with historical data when there wasn't a fault, and try and confirm that the gas levels haven't increased by more than 50%, because you really need that increase to give you some confidence that a fault is occurring.
Okay, so the next question is, if we have online monitoring, what are the key gases to monitor in terms of corrosive sulphur?
Well, that's a good question. I would look at the heating gases, so methane, ethane, ethylene, and if any of these are elevated above typical levels, say according to IEC 60599, then you can follow this up with a corrosive sulfur test. And that's one of the tests that you should follow. If you see heating in a transformer, look at the electrical test results, recent electrical test results. If the levels continue to go up at a high rate, you need to think about taking the transformer offline and doing electrical testing. You can also do thermography to look for problems like overheating of the tank, particle count testing, but yeah, do the corrosive sulfur test if you see elevated levels of methane, ethane, and ethylene.
Okay, so the next one is from Alf, and it was, once sulfur has been found and oil has been treated, does the continued presence of sulfides mean that the transformer is to be taken out of service? Also, is there some experience on how long a transformer lasts in terms of years once the sulfides are present?
No, we don't have that information in terms of how long it will last. Certainly, if you passivate the oil, this can prevent any further reaction of the likes of DBDS with the copper windings. And that's good, that's a positive thing, but it doesn't deal with any problems that have already occurred. But But you really need to do, when you add the passivator, test the passivator levels every year. If you see levels decreasing, add more passivator. And if after a couple of years the levels continue to decline, then you really need to think about the oil change.
Okay, and Sherwin has asked, is it advisable to conduct a DGA analysis for transformers not in operation for a long period of time? And are the DGA results still valid?
If the transformer's offline, then really gas generation levels shouldn't increase. You should do oil testing still on transformers that are offline, but really the focus is looking at the moisture levels to see, and also we'd look at the dissolved gas analysis levels to look for changes in the oxygen levels in the oil. So hopefully, for instance, if the asset is hermetically sealed, any changes in the oxygen levels could indicate that there's some problems with gaskets and oxygen's getting into the transformer. And regardless of whether the transformer's online or not, we need to keep oxygen levels low and also the moisture levels low as well.
Okay, so the next question is, should we do dynamic resistance tests regularly on the on-load tap changer?
Electrical testing of tap changes is not really my area of expertise, but certainly you would do this type of electrical testing during shutdowns, maybe every 3 years, or it really depends upon the number of operations according to recommendations from the manufacturer as well. If there are no problems identified by the dissolved gas analysis, then it's kind of questionable whether you would do the testing, but certainly it's one of those tests that you can think about doing if the dissolved gas analysis indicates problems.